All right, thank you very much. So let's continue our discussion on structured protoplanetary disks. So as we've seen in Nita's talk and some of the other talks today, that protoplanetary disks are full of structures. So what created those structures? We're not too sure, but certainly one exciting hypothesis is they're produced by embedded planets that are forming in those disks. So in this talk, I will try to provide an update on this topic, the connection between disk structures and planets. So most of the results are based on ALMA and VLA observations. And towards the end, I will also talk about what we expect from SKA and ngVLA in this field. So first, a very simple question. So why do we think there may be planets behind disk structures? The idea is very simple. So planets are gravitational perturbers. So in disks, they can gravitationally perturb the material distribution and may produce structures. We call this process gravitational disk-planet interaction. So here I'm going to show you a movie that will give us an idea of how this process looks like. So this movie is from a hydrodynamic simulation and will show the time evolution of the surface density in a disk perturbed by a 1 Jupiter mass planet here. So the movie will be in a frame co-rotating with the planet. So let's start the movie. All right, so once the planet forms, it quickly launches a bunch of spiral-shaped density waves, and then the planet removes material from a orbital region to open a gap, a low-density annulus structure, and then the inner and outer gap hatch become making trouble this time. Okay, so the inner and outer gap hatch become unstable, and then two large-scale asymmetric structure form. So while the planet is faint and tiny and difficult to see next to the bright star and the big disk, those planet-induced structures can be much more prominent. So if we can directly see them in observations and convince ourselves they are produced by embedded planets, they can be the signpost of planet formation. In a way, this is similar to how we identify planes on the sky sometimes. So here in this photo, we know there is a plane, even if we cannot directly see it because the plane leaves behind a tail. So in protoplanetary disks, planets are the planes, and these gravitationally induced structures are the tails. All right, the four most basic questions in the connection between a disk structure and planets are: first, is disk-planet interaction able to produce observed structures in disk? And then what kind of planets are we talking about? And next, if we think structures are produced by planets, what can we learn about those planets from disk observation? And finally, do we really have evidence to say that disk structures are produced by planets? So first question is, at least in theory, is disk-planet interaction able to produce observed structures? Well, here are here are three images of the same disk MWC75A on the same scale, but at different wavelengths. The first panel shows a near-infrared scatter light image, which has a pair of grand design arms at tens of AU in a sort of M2 rotational symmetry. The middle and right panel shows ALMA and JVLA millimeter and centimeter emission maps. In the ALMA map, we see an inner ring, an outer ring, and on top of them, two emission clumps. The northern ALMA clump also has a centimeter emission counterpart, which we see here. The southern ALMA clump, however, doesn't have a clear counterpart. This source here coincided with the location of the star. These images look different primarily because they're at different wavelengths, so they trace different disk components, right? So very roughly speaking, let's say observations at a given wavelengths roughly trace the distribution of dust corresponding to the same size. So all these structures may be produced using two giant planets, one inside and one outside in the system. So at the bottom, I'm showing you synthetic observations made from disk-planet interaction models. They're produced using hydrodynamic and radiative transfer simulations, and they represent how we think planet-induced structures should look like in a real observation. So the first panel shows if we put a multi-Jupiter mass planet on the outside, it is able to drive a pair of grand design arms inside its orbit in scatter light, very similar to this. The same planet also opens a deep gap, and the inner gap edge becomes so-called Rossby unstable. And the consequence of the instability is the production of a vortex. A vortex in a protoplanetary disk is like a tornado, and it sucks millimeter-sized particles to its center. And just to recall, millimeter emission traces the distribution of millimeter-sized particles. Therefore, this vortex look like a millimeter emission clump. And a second planet, less massive but still a driven planet, is invoked in an inner disk at 35 AU. It too opens a gap, triggers formation of another vortex, and we see a second emission clump in the synthetic ALMA image. The northern vortex is also good at collecting centimeter-sized particles, which is why we see a centimeter emission clump here. The southern vortex is already in the process of decaying in the simulation, so it doesn't collect centimeter-sized particles as well. So long story short, in this multi-wavelength observation of a disk, we see a variety of structures that can be produced using 2 planets. All right, what kind of planets are behind disk observations? So the previous example showed us giant planet can do the job. What about small planets? As it turns out, low mass planet as low mass as super Earths can also produce detectable structures using ALMA as long as the disk conditions cooperates. So here I'm going to show you a movie which will show the surface density evolution of millimeter-sized particles, the kind of particles probed by ALMA, as a disk is being perturbed by a 10 Earth mass super Earth. So let's start the movie. Planet launched a bunch of density waves and opened a bunch of narrow dust gaps. Now you may wonder, you say this picture looked qualitatively different from the previous ones we saw, in which a giant planet opened one big gap around its orbit. It's true. So the primary difference is one, this model has a very low mass planet, super Earth, and also the model has a very low viscosity. The Circumstellar of alpha is 5 times 10 to the minus 5. So do we really expect to see this kind of low mass planet opening multiple gaps and producing narrow dust rings in low viscosity environment in the real universe? Well, this is the ALMA observation of HD 169142 in dust continuum, and in the outer disk we see a set of narrow dust rings and sandwiching 2 narrow dust gaps. And this is a synthetic observation of a disk model which has a mini Neptune, sort of a dozen Earth mass or so at 60, 70 AU. It is able to reproduce the observation. All right, if we think planets are behind disk structures, what can we learn about them? Well, intuitively, you might think the morphology of planet-induced structures should depend on the property of the planet, right? If we change, for example, the mass of the planet, we expect the gravitational induced structures to change accordingly. If you can quantify the relation between the two, you may find a way to infer the property of the planet from disk observations. So here I'm going to show you a movie that will tell us the steady state solution in the gas surface density as a disk is being perturbed by a planet. This time we're not going to look at time evolution. Instead, we're going to make the planet to become more massive as a movie goes, and we'll see how the structure evolves. So you can see the planet mass becomes more massive. So it started from a sort of Saturnish mass and goes to a multi-Jupiter mass. So as the planet mass increases, a few things happen, right? You see the planet opens a deeper and deeper gap. The radial width of the gap also become larger. You can see the gap become wider, right? And also the spiral density waves become more prominent. Their contrast increase with respect to the background. And finally, this is more subtle, the azimuthal separation between the 2 spiral arms also increase. You can see at the beginning, they're very close to each other, but towards the end, they're sort of in a 180-degree away configuration. So all these correlations can be used to infer the mass of the planet. We call them dynamic mass constraint if you think you know the parameters of the disk. And if you apply those relations to real samples of disk observation, you can infer a population of planets forming in disks. So here is one of such examples. We're looking at planet mass as a function of semitic axis. All these gray dots are mature planet found in radial velocity and transit observation. And those colorful dots are inferred from structured disk from the observations of those structures. And we got 10 Jupiter mass here, 5 Earth mass here, and 10 AU and 100 AU here. So roughly speaking, what kind of planets are behind observations? Well, at the moment, they're super Earth to multi-Jupiter mass planet at 10 to 100 AU. And finally, our observed structure is really produced by planets. Well, at least in some of them, they are. So the best example is a system called PDS-70. So here we're looking at, on the left, we're looking at 3 observations of the PDS-70 disk. The first is a near-infrared observation. We see a ring-like disk, a cavity, and a point source marking the location of a planet PDS-70b. The middle panel shows the H-alpha image of the cavity region. So 2 H-alpha emitting point sources are detected inside the cavity, then interpreted as 2 accreting planets. And then the right panel shows the ALMA high-resolution observation dust continuum map, and then the millimeter counterpart of one of the planet PDS-70c is detected, most likely tracing circumstellar circumplanetary dust emission. And then the right panel shows a synthetic model of the system in ALMA dust continuum with 2 planets, and together they can indeed reproduce the observation, a ring-like disk plus a cavity. So the good news is PDS-70 shows at least some systems, the structures can be explained using planets, but the not so good news is such systems are still very rare. So near-infrared direct imaging observations have been attempted for many tens of disks with structures to look for the predicted planets, and so far we only have perhaps, you say, less than a handful of detection. How to interpret all this non-detection is still under investigation. All right. So just to summarize this part, is disk-planet interaction able to produce observed structures in disks? Yes. What kind of planets are we talking about? Super-Earths all the way to multi-Jupiter mass. What can we learn about those planets from observations? We can constrain their mass and also their location if we can characterize the disk morphology and know the disk parameter. Are observed structures really produced by planets? At least in some systems, we get a confirmation, but those confirmations have been quite difficult at the moment. All right, moving forward, where do we go from here? So in the short term, before the next generation of telescopes hit the sky, one avenue that people are exploring right now is to connect planets with disk features, not just using observations of a disk at a single wavelength, but to use observations, multiple observations of the same disk at multiple wavelengths, and particularly tracing different structures produced by the same planets. So just to explain, so here is the planet population forming in disks that we already saw. Most of these predictions, those blue dots, are made using gaps in disks. So to the zero starter, let's say you see a big gap in a disk, you're sticking a planet. That's roughly what it is about. So when Jupiter mass is here, so you can see there are quite a number of Jovian planets at tens of EU for those gaps. So in theory, Jovian planet at tens of EU are also supposed to produce other type of structures, for example, spar arms. So here are 2 images showing synthetic near-infrared scatter light and synthetic ALMA millimeter continuum emission maps of Jovian planet at tens of EU. Sure, you see the gap, but you also see the spirals pretty clearly. So whether those predicted gap opening planets are producing the expected spirals is a test. So very recently, here is an example. In the HD 169142 disk, here's a scatter light image. There's a gap, and a planet candidate was found a while ago. You may say, well, you know, this planet looks faint. I'm not too sure whether it's real or not. But lately, observers were able to pull the signal of the outer spiral excited by the planet from the observation. So now we're looking at a planet with its gap and its spiral. So that makes the observation, the evidence more comprehensive. So in the long run, of course, we have ngVLA and SKA, and I have 2 examples to show you what we're expecting from those 2 instruments. You know, of course, we're expecting a lot, but here I think there are 2 fairly important points, which have also been mentioned earlier today. So here is a simulated ngVLA 7mm emission map of a system with a 10^-10 mass planet at 3 AU. You can clearly see the gap and the mutually asymmetric structures. Here's the same disk model, but if you observe with ALMA at millimeter and with ALMA's best angular resolution, you can kind of see something there, but all the details are missing. So with ngVLA, we'll be able to trace the formation of planets, super-Earths in a terrestrial planet forming region, and that's not something we can do at the moment. And also this will enable monitoring of orbital motion of these structures, which we also cannot quite do at the moment, because all those planets are at tens of AUA. And what about SKA? Okay, so here's the iconic ALMA millimeter image of the HL tau. If you think it's different from the ones you used to look at, that's normal because this is a deprojected one, so all the rings are circular, right? And this is a model produced to explain the observation. So 3 Saturn-ish mass planet can roughly explain what we see in the ALMA observation. And then this is the corresponding synthetic SKA image at 2.4 centimeter. You can see the matchup here. So upon first looking, you might say, okay, what's a big deal, right? You can already use ALMA to see those gaps and rings, and they already enable you to make connection to planets. So why bother going with SKA to longer wavelengths? Well, for those of us who are interested in planet formation and disk observation, going to longer wavelengths makes all the difference, because with that, you can probe more particularly thin emission. So here you're looking at opacity as a function of wavelengths for a bunch of dust models. Here's the centimeter wavelengths. So all these models predict dust opacity should go down with wavelengths from ALMA to SKA's wavelengths. Therefore, with SKA, we're working in a more optically thin regime, and that helps tremendously in terms of detecting structures in dense region. So here are 2 synthetic disk models. They're practically the same with the same kind of planet, except the left one has a low optical depth, is optically thin, and the right one is optically thick. So the planet opens a dust gap, that's cool, drives the density wave. It is quite visible in the optically thin case, but everything is, everything disappears in the optically thick case, right? Because in that case, you're looking at the disk photosphere and all the density structures are hidden beneath it. So with that, I will stop and take questions. Thank you very much.
Okay, questions from the audience? Okay, it's over there. This one.
Hi, thanks for the really interesting talk. It's completely outside of my field, but I'm wondering, at a population level, how do the masses and other parameters of the planets that you infer from dynamics compare to the properties from, say, radial velocity or transit surveys?
Yeah, excellent question. So that's a question we're also very interested, but unfortunately there's no answer at the moment, because radial velocity and transit mostly discover close-in planets. They're within a few AU, but with those disk imaging-based observation, we're mostly talking about tens of AU planets. So the parameter space don't quite overlap at the moment.
Robin, that was a great talk. My question is about is the potential for degeneracy in the solutions of which planets fit which disks. So you're showing us cases where I presume the minimal number of planets are being used, right? But if there were, for instance, a very wide gap with several smaller planets in it, it would perhaps explain why we don't see the planets as easily. Could you comment on sort of, obviously you're saying that the more information we have, obviously the less you beat down the degeneracy significantly. Could you comment on whether that's a plausible explanation for a lot of these non-detections of the planets?
Of course. So indeed, there are many, well, maybe I shouldn't trash my field so much. So there's some degeneracies in the models. For example, in plots we see here, you see there are no error bars being plotted. And that's, I think, partially because we're not too sure how to characterize those error bars. And for some of them, error bars could be pretty large. And to explain the non-detections, you could try to invoke a lower mass planet, and that's indeed one possible solution for some of the systems. But for some others, the gaps are quite narrow. It's difficult to fit in multiple planets. So for those, it's less clear what the solution is.
Thank you. Also, it's not my field, but I'm very curious. In addition to the planet mass, what other properties could be produce a discernible effect, like the spins or something like that?
Right, so spins will indeed be very interesting to know if we are able to constrain, but I'm not too sure if we have any way to constrain the spin. The other parameters that we can possibly constrain include orbits and also like eccentricity and inclination of the planet with respect to the disk. So essentially, parameters related to mass and orbits.
There's an online question from Bezad Bojnori. You showed that the model can successfully produce the observation, but have you studied other possible models that can also produce the same observations? How diverse are the models?
Absolutely. So in our field, people run 5-day conference just to talk about alternative mechanisms. So long story short, there are many other alternative explanations. So for some of the disk images I showed, planets is indeed not the only one. For certain particular characteristic structures like the multiple narrowly spaced dust rings and gaps, it looks like other mechanisms may have trouble, and planet could be the best hope for now.
So Rubing, that was very nice, but that was all on the dust continuum. Can you talk just a couple of words about gas kinematics? There's a nice poster in the back about CO at 1 to 0, and so I'm wondering whether there's a niche there for at least the ngVLA.
Yes, gas kinematics is a thing that has really picked up in the past couple of years, and lots of people in the field are looking into that. So if you see essentially non-Keplerian rotation in the disk, that may indicate the presence of gravitational perturber. I believe ngVLA would be quite helpful in that front as well. I haven't looked detail myself. So.
Okay, well, the very last question.
Thank you. Also, thank you for a very nice talk. It's also completely out of my field. But I was also curious, following up on the questions. So with these extremely nice images that you will be able to get with the ngVLA and SKA, what will actually be the limiting factor? Will it be on the uncertainty, for example, on the planet mass? Will it actually be the model uncertainty, or is it still the data that is the limiting constraint here?
I think that degeneracy in the model would unfortunately be there for a while. The real key thing we can try to do to eliminate the model is to constrain the disk parameters better, particularly the viscosity or turbulence level in the disk. That's something we really struggle, and that affects all the planet prediction. And hopefully with ngVLA and all this future instrument, we'll be able to constrain those parameters better. Maybe Ninka has something.
I think this has to be the last question, because otherwise we'll be late. But clearly a lot of interest, and people got the sugar rush now, and we are awake. So thank you. Let's thank Robin again. So the next